The electromagnetic spectrum includes all these different types of energy that radiate as a wave. And you can't see most of these types of radiation. We can't see gamma rays, X-rays, or UV. We can't see infrared, microwaves, or radio waves. But you can see just a very small portion of the energy on this spectrum. We can see visible light, which is why it's called visible light. And so what makes these types of radiation different and what makes them the same? Well, first of all, we know that they're all waves. They're all waves that radiate from a point, and they have wavelength and frequency. But what makes them different is that they have different wavelengths and therefore different frequencies. Gamma rays have the lowest wavelength and highest frequencies. Radio waves at the other end of the spectrum have the longest or highest wavelengths and the lowest frequencies. And then you have all the different waves in between with variable wavelengths and frequencies. Wavelengths of these types of radiation measured in meters and usually with a metric prefix associated with it. For instance, if you're reporting the wavelength of a gamma ray, this is gamma rays are in the region of 10 to the minus 12, which is the metric prefix pico. So a gamma ray measurement might be 5 picometers. Microwave is in this region, which is 10 to the minus 2. So a microwave, instead of having 10 to the minus 2 meters, the wavelength can be reported as 5 centimeters, because centi is 10 to the minus 2. Radio waves are in this region, which is 10 squared meters, or 10 to the 2 meters. So a radio wave can be reported as something like 5 hectometers, because hecto is 10 squared. So we can see that visible light is reported in the wavelengths of nanometers. Nano is 10 to the minus 9, so this would be 500 nanometers. So the wavelengths of visible light are between 400 and 700 nanometers, which would be 400 times 10 to the minus 9 meters, or 700 times 10 to the minus 9 meters. So we already talked about wavelength and frequency being inversely proportional. If one is high, the other is low. If one is low, the other is high. Well, this is because of the relationship in this equation, where wavelength times frequency are multiplied and always equal to the same value, which is equal to c. It's represented by c, which is the constant for the speed of light in a vacuum. So the value for c is approximately 3 times 10 to the 8th meters per second. Now that's a constant, so all constants have infinite significant figures, so don't look at this constant value. Don't look at this as having one sig fig. It's actually infinitely significant because it's not a measured value. You can use this equation to solve for one unknown out of the 3, but you always are given either the wavelength or the frequency, and you always have this constant value for c. You just need to remember that although it's represented by a variable, although it's represented by the letter c, you have that number value. It's not an unknown. This is another equation we'll be using, which is to calculate the energy of a wave when you're given the frequency. This equation also has a constant value in it represented by the letter h. Now h, and similar to c. Why is it c? Why is it the letter C and it should be S or L because it represents the speed of light? And why is this H? This H represents this number that's called Planck's constant. So why is it H? I don't know. But just know that even though it is a letter variable, you are given the number. You always have that number value. It is not an unknown. So the number value you can look up. You will be given it, but it is 6.63 times 10 to the negative 34. And this is the units of J, which stands for joules, and times seconds. So this is J times S. And this, you should notice, is a very, 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 very small number. 10 to the minus 34 means that there are 34 zeros and a decimal in front of 663. So that's a really, really, really small number. So what that means about the relationship in this equation is that you take this h value, which is a really, really, really small number, and multiply it times frequency to get energy. frequency is basically directly proportional to energy. If you have a high frequency, you'll have a high energy. Or if you have a low frequency, you'll have a low energy. So we have these two equations that we can use for calculations, but also to understand the relationships between wavelength, frequency, and energy. We know that energy and frequency are directly proportional. If one is high, the other is high. Or if one is low, the other is low, and this is from this equation. And wavelength and frequency from this equation, these are inversely proportional. If wavelength is high, then frequency is low. If wavelength is low, then frequency is high. When using this equation to calculate energy, you'll see that Planck's constant has the units of joules times seconds, and the units of seconds will cancel out with the frequency, which is 1 over s. So what you're left with is that energy will have the units of joules, or J. Now, energy can also have other units, like calories we'll see in a future module. For electromagnetic radiation, the calculation ends up with the units of energy as joules. Light is actually interesting because it is a wave. It's an energy wave, but Einstein famously studied light and reported that light can act like a wave and also a particle. It's called the dual nature of light, and Einstein won the Nobel Prize in 1921 for describing this. That particles of light, when you can think of light not only as a wave, but sometimes as individual particles, which is unlike any of the other forms of radiation. No, microwaves don't do this. UV rays don't do this. Just light. Light energy can act as a wave or a particle, and those particles of light are called photons. So you will sometimes see that designation, that light energy can be called a photon of energy.